Hello everyone. Today we're going to talk about circles and the angles within and on and outside circles. We're going to do so in an intuitive way, not using formal proofs, but hopefully in a way that's going to make sense so that you're not just memorizing these things, but they can kind of stick in your brain due to the fact that you understand them at a conceptual level or at least that intuitive level. I certainly encourage you to look up the formal proofs because it can only help you, but again, we're not going to do that here. So to start off, just recall what an inscribed angle is. This looks to be about 90 degrees in terms of the arc it makes. So this arc, we could call it arc A, appears to be about 90 degrees, which would mean that this angle here would be 45 degrees. So an inscribed angle is half of the arc it makes. Just from that intuitive lens, if we were to look at this central angle within its inscribed angle, but they're attached to the same arc, so this arc A here, they make the same arc, it makes sense that this central angle would be exactly the same as that arc at 90 degrees or a quarter of a circle. And then visually, it also makes sense that this angle here would be about half of that. And it turns out it's exactly half of that. So that's really all you need to know is this relationship between the inscribed angle and the central angle and the arc to understand these other two theorems that often give people trouble when they try to memorize stuff, because students will often go, well, I'm not sure when to add the two arcs or subtract the two arcs. So that's what we're going to look at. But to get there, we just have to recall that an inscribed angle is half of the central angle or half of the arc that it shares with that central angle. So if we have this situation here where the point of intersection of two lines is on the circumference, we can say that this angle x, or the angle made by those two intersecting lines, is exactly 1/2 of arc A. And that's just this inscribed angle theorem again. If arc A is 90 degrees in this case, then our angle over here would be 45. 45 because of arc A being 90. So x is exactly 1/2 of arc A. So the measure of angle x is arc A divided by 2. So if we were to just grab the circle and move that point of intersection away from the circumference, we're going to move it inside the circle, or I'm going to essentially move the circle to the left. Look what happens to the size of arc A, to that arc on the right. What's going on? Well, it's getting smaller. And as I move that point of intersection back to the circumference of the circle, arc A is its original length. So if I was to draw the length of arc A, let's keep that color white, and I'll grab a pen. We'll use the color green. I'm going to try to draw as best I can, trace that out. You can clearly see as I move the circle to, if I move the circle to the left, if I can grab the circle, now it doesn't want me to be able to move it. There we go. The arc A gets smaller, and I'll trace it again. So once I move it back, we'll begin to see the size difference. Okay, so arc A clearly gets smaller as we move that point of intersection inside the circle. But what happens here on the left? Well, a new arc is formed. Let's call that arc B. So again, we've got our angle. It's right here. We're going to call it angle X. As I move the circle so that the point of intersection goes inside the circle, and by point of intersection, just to make sure it's clear, what I'm referring to is where the two lines intersect. So this green point right there. Arc B grows on the left. This new arc grows at exactly the same rate arc A decreases. So right here, arc A has all of the angle X's relationship. And as I move the circle to the left, arc B grows as arc A decreases. So when we add those two arcs together, if I was to go, you know what? I'm going to add arc A and arc B together, those measures of those arcs, what that does is basically almost exactly like saying, I'm just going to move the circle so that the point of intersection is actually on the circumference of the circle. And again, we remember in this case that x, the angle x, is exactly half of its arc A. So we would just divide by 2. So why are we adding arc B and arc A when we have situations like this? Well, we're adding the two arc lengths because it's like the same thing as the inscribed angle theorem. It's kind of like moving that point of intersection to the circumference. So just to make sure this is crystal clear, we've got these two arcs here. We've got arc A on the right and arc B on the left. And if I was to add arc B to arc A, it would be the exact same size as arc A if the point of intersection was on the circumference. So those two, whoops, let me get the colors right here. And I'll use green again. If I was to somehow grab this orange line and try to rotate it around, and I didn't do a very good job of drawing it, and I was to attach it to this line, I wonder if I can just grab the green line. Yeah. These are the exact same length. What do these two orange lines represent? Well, they represented the length of arc B and arc A at the position where I drew them, crudely drew them. We can make that look more like an arc. So combined, they total the arc that would be formed if the point of intersection was on the circumference. And so again, we're just using the inscribed angle theorem here. The fact that when this is, when this arc is 90, this angle is 45. We're just using that to come up with this theorem right here, that angle X equals both arcs added together divided by 2. So what happens then if the point of intersection is not inside the circle, but outside the circle? Well, we can use the exact same logic. In fact, let's just do this kind of the same thing. Let's drag that point of intersection around and see if we can't make some observations. So let's move the circle again. So here's where the point of intersection is inside the circle. We would add the arcs to get this situation, and then we would divide by 2. But what if I was to reposition arc A over here? Maybe I'll move arc B over here. If I was to just keep dragging the circle such that the point of intersection ends up outside the circle. So here it's on the circumference. Now the point of intersection's outside the circle. What's happening to arc A? Well, arc A is getting too big. You can see arc A is getting huge, actually. And as I move back to the left, arc A shrinks. All the way till, okay, arc B is 0 now. And now the point of intersection is inside the circle. But as I move this way, I have arc A, 0 arc B. Now arc B starts coming. It starts forming. It has a measure now. That's arc B, this little tiny amount of the circle right here. That's arc B. And we have this large arc A here on the right. Well, as I move the circle to the right even more, arc A continues to get larger, but at the same rate arc A is growing, arc B is growing. And we want to know how long would it be if the point of intersection was right on the circumference. So if you have a situation like this, and the textbook or your teacher or somebody is asking you for angle X, or this angle right here, it makes sense then to go, you know what? That angle X is going to be equal to arc A, or the large arc, minus the smaller arc, arc B, divided by 2. Because this arc A is too big when the point of intersection is outside the circle. But it just so happens it's too big by exactly that amount. So I'll actually change color here to red. And if I was to try to drag just this red line here, oops, that's not what I want, just the red one. It may not let me. Well, let me just drag this circle back to the circumference. This arc right here, this green arc, this is exactly too large. This arc right here, that's exactly too large by the same amount arc B, by the same degree measure of arc B. So when we subtract them, it's like taking that point of intersection to the circumference again. And so you divide by 2. So if the point of intersection's inside the circle, you're going to have to add your 2 arcs and divide by 2. and that's going to equal the measure of angle x. If the point of intersection is outside the circle, the measure of angle x is equal to the large arc minus the small arc divided by 2. But all this is doing is relating the measurements to the central angle theorem, or I'm sorry, the inscribed angle theorem, where this angle is exactly 1/2 of the arc. So in its totality, it makes a lot of sense that we would have these two equations to describe the relationship of the angles when we understand that this is true, that this angle is 1/2 of the arc. All right, thanks for listening. I hope that helps.